Hey guys, so in this video we're going to cover literal equations, and so your I can statement is to solve literal equations for a specific variable. And just to kind of give you a brief definition, literal equations are equations that have several variables, and since we only have one equation with several variables, we're not going to end up with one specific numerical value that a variable will always equal. For example, in 4x equals 20, we know that x is 5, and that doesn't change because there's one variable in one equation. However, what you're about to see are one equations with two variables, and so they really represent more of a relationship than a specific given value. All right, let's get started. So to best help you understand this, I'm just going to do three examples. And given this particular equation right here, d equals m divided by v, it's already solved for d, right? d equals the relationship of whatever m is divided by whatever v is. And we can use literal equations to express relationships we see in the real world, that we see in nature, whatever, properties of physics, and we don't necessarily always have to have specific values. We can just, plug in the equation. So you guys might know from physical science some literal equations, force equals mass times acceleration, stuff like this. So we want to know how to rearrange these, though. We want the math skills to be able to do equations like this, specifically for science. So if we're going to solve this for m, we want to get m isolated by itself. So one thing that we could do is we could multiply both sides of this equation by v. And the reason I'm going to multiply both sides of this equation by v is because you'll notice that if I turn v into a fraction, v over 1, that these two cancel each other out. And so I'm left on the right-hand side with just m, and the right-hand side I've got v times d. So m equals, so I'll rewrite this up here in a neater fashion. So in this example, m equals dv, or vd, it doesn't matter. And that shows a relationship that if d equals m divided by v, then m must equal d multiplied by v. So it's a relationship. If we use regular old numbers in here, and we said that 5 was equal to 10 over 2, then we could rearrange that to say that m, which in this case would be 10, that 10 would also be equal to 2 times 5. So that's all we're doing. We're solving for a specific variable in a situation where we have lots of variables. Here's another example, and this is a very special equation that you'll learn more about because it's the linear function, and it's called slope-intercept form. But in this case, we want to try and solve for b, and we'll learn all kinds of things about this equation. But let's talk about solving for b. So we want to get b by itself. Well, there's one term besides b. B. It's this mx, right? So if we could get that to the other side, if we could take that out of the way, we would have this thing solved for b. So let's do that. So let me rewrite this. Y equals mx plus b. So if we subtracted mx from both sides, we would end up with negative mx plus y equals b, because mx minus mx would be 0, so we just have b on the right, and we've got the negative mx term over here on the left now. We could rearrange this if we wanted to write y minus mx equals b. This is the exact same thing. And we could rearrange it further to say that b equals y minus mx. So, but once you get to this form, I mean, this is the correct answer. These two things that I'm pointing at here in this red color, these are sort of optional, just to sort of arrange it in such a way that you appreciate or you can tell better. So we're used to seeing the variable that we solve for on the left, so sometimes it's nice to arrange it in that way. Sometimes we don't necessarily like to lead with a negative, so we can rearrange the terms so we're not leading with a negative when possible. So let's just take a step back, though, and I'm going to actually give you a trick now, okay? I'm going to solve the same problem, but I'm going to give you a trick, and I haven't told you this trick yet because I want you to understand why it works. But you can essentially take any term in an equation, and you can move it to the other side of the equal sign as long as you change the sign of the term. So this term over here, mx, is positive on the right. So when I move it to the left, and I could even move it right here before the y, it doesn't matter, it's going to become negative. So I can go straight into this form, just like that. That's how people do stuff quickly with equations. They figured out that trick, where you just, if you want to move a term, you just change the sign and move it across the equal sign. All right, guys, let's do one more example to help us out with this. So in this last equation, for our last example, we want to solve for x. And so this is what we want to solve for. We also have a secondary variable of b. So again, we're going to end up with the relationship for x, not a specific number. So let's go about doing this. So 2x, whoops, got a reminder here. Hold on, let me close it. My iPad reminded me of something that threw me off. So we have 2x plus b equals 13. Now let's follow the trick that I just specified in the last example. Let's take a look at the term that's in front of our x, and let's just move it over here. Now if you remember, the trick was to identify its original sign, so it's positive over here, and then when we move it across the equal sign, change the sign of the term. So we can say, okay, 2x equals 13 minus b, because it was positive on the left, so it's going to be negative on the right. And you might be wondering, okay, that's a great trick, but why does it work? Well, again, it works because we're subtracting b from both sides. They cancel each other out on the left, and you have negative b on the right. But now we still aren't quite solved for x because of this coefficient of 2. So as you guys know, to get rid of that coefficient of 2, all we got to do is divide by 2. So we're going to divide every term in this equation by 2. We're going to divide the left side and the right side. So we can say that x is equal to 13 minus b over 2. Or you could write it this way. X is equal to 13 over 2 minus b over 2. These two parts right here that I'm circling in red, these are equivalent. You can split a fraction that has a common denominator and two things in the numerator. You can split that into two separate fractions, or you can just leave it as one division problem. It doesn't matter. And I'm not picky. Any one of these forms I would consider correct. So anyways, that's the examples, guys and girls, and I want you to think, okay, this is showing me a relationship. I know now that x is equal to 13 minus whatever b is divided by 2. It's a relationship, not a specific numerical value. Okay, the last thing I want to show you here is on the next slide, and it's a challenge problem, and I think it'd be cool if you'd try it. Try it and try to come into class with it solved. Here's that challenge problem I mentioned. Can you solve for m in this particular equation? All right, give it a try, guys. And you know what your homework is tonight. It's just those 5 problems I gave you in class. Good luck. Bye.